Hi students, in this class we are going to study the modeling of long transmission lines. First of all, let me tell you why we should study the modeling of long transmission lines. Suppose a consumer needs 11 kilovolt at the receiving end. Now we need to find out how much voltage should be generated. Suppose the voltage drop in the transmission line is 0.5 kilovolt. Now the generator should produce 11 kV plus 0.5 kV. So 11.5 kV should be produced. So in order to find out this voltage, you should know what is the voltage drop in the transmission network. For that you should know the structure of the transmission line. For that you should study the modeling of transmission networks. Based on the length and operating voltage, we can classify the transmission lines into short, medium and long lines. In this class, we are going to study the modeling of long transmission lines using rigorous method. Suppose this is the transmission line we are having. This is our receiving end side and this is our sending end side. Suppose the total length of the line is L meter. And assume Z is the impedance of the transmission line per meter length. So total impedance is Z into L. And Y is the admittance per meter length. So total admittance is Y into L. Now let's consider a small portion of the transmission line. Suppose this is at a distance of X meter from the receiving end side. When X is equal to 0, we reach the receiving end side. When X is equal to L, we reach the sending end side. Here X is the variable, is the distance of the transmission line from the receiving end. And in this particular section we have certain impedance. This is the impedance of the line, even though it is represented by a resistor. Impedance per meter length is Z. Now suppose this transmission section has a length of dx meters. So impedance of this section will be impedance per meter into the length. Similarly, we have a capacitive admittance in this section. Even though this is represented by a resistor, it is the capacitive admittance. Admittance per meter length is Y. The length of this section is dx. The total admittance is Y into dx. Suppose the voltage at the right side of this section is V and the voltage on the left side is V plus dV. As you know, when we move leftwards, the voltage increases, and when you reach the leftmost position, we get the voltage Vs. So you know this dV is dropped in this part of the transmission line. The current at the right side is I amperes. The current at this part is I plus Di. Now what happens to this Di current? Obviously it flows through this shunt admittance. Now this dV equals, actually this dV is dropped in this part of the line. Voltage drop equals current into the impedance z dx, or you can write dv by dx is equal to I into z. Similarly, this di equals is the current flowing through this shunt admittance, voltage by reactance, or it is voltage into admittance of the capacitor, y into dx, or di divided by dx is equal to v into y. If you differentiate this expression, it becomes d square v divided by dx square equals z into di by dx. Di by dx equals v into y. That is z into vy, or it is equal to yz into v. So d square v divided by dx square equals yz into v. This is a differential equation. The solution for this expression is v equals a constant k1 into cos h x into root of yz plus another constant k2 into sin h x into root of yz. X is the distance of the line from the receiving end, y is the admittance, z is the impedance of the network. Now we got an expression for the voltage. Similarly, we have to write an expression for the current. From this equation we can find an expression for the current. Zi equals dv by dx. Zi equals dv divided by dx. It is equal to the differential of this voltage equation. It is k1 into the differential of cos h ax equals sin h ax. You can remember a couple of differential formulas. D by dx of cos h ax is equal to the constant a into sin h ax. Similarly, d by dx of sin h ax equals the constant a into cos h ax. So the differential term is k1 into differential of cos h ax, constant is yz, into sin x root of yz plus k2 into differential of sin h ax. Root of yz is constant, cos h x into yz. Here the variable is x, that's the distance of the line from the receiving end. Or you can write I equals, this z can be brought to the right side. When it comes within this root, it becomes 1 by z square. It is k1 into root of y by z. One z will be getting cancelled, into sin, it is sin h x into root of yz plus k2 into, again when this z comes within the root, it becomes 1 by z square, y by z into cos h x into root of yz. Now we got an expression for current also. So we got one expression for voltage, one for current. But in this expression we have constants k1 and k2. First of all, we need to find out the constants. When you apply this boundary condition, that is x is equal to 0, we reach the receiving end side. Here we will get the constants k1 and k2. So we will apply this boundary condition x equals 0. So the voltage becomes the receiving end voltage. The current becomes the receiving end current, IR. So VR equals K1 into x equals 0 cos h0 equals 1 plus K2 into sin h0 equals 0. So K1 equals VR. The second equation, when x equals 0, the current becomes receiving end current. IR equals sin h0 equals 0, that is 0 plus K2 into root of y by z cos h0 equals 1. So K2 equals root of z by y into IR. Now we got K1 and K2. If we substitute these values in the voltage and current equation, V equals VR into cos h x into root of yz plus K2 into sin K2 is equal to root of z by y into IR into sin h x into root of yz. The current equation is I equals K1 equals VR into root of y by z sin h x into root of yz plus K2 equals root of z by y into IR into root of y by z into cos h x into root of yz. So here this root of z by y and the root of y by z getting cancelled. So the current equation becomes VR into root of y by z sin h x root of yz plus IR into cos h x into root of yz. Now we got one expression for the voltage and one expression for the current. These are the general expression for voltage and the current. If we apply this boundary condition, that is x is equal to L, we will get the sending end voltage and the sending end current. That is our objective. In all modeling problems, we need to find out sending end parameters. So here we put X is equal to L. So V becomes Vs and I becomes the sending end current. So Vs equals VR into cos H, this X equals length L into root of YZ plus IR into root of Y by Z sin H, X equals the length root of YZ. The current IS equals VR into root of Y by Z into sin H, X equals length root of YZ plus IR into cos H L into root of YZ. Here this length L can be brought within the root. You should remember L into Y equals, Y is the admittance per meter, L is the total length. We'll get the total admittance of the line. Similarly, L into impedance per meter will give total impedance of the network. So Vs equals VR into cos H. When L is brought within the root, it becomes L square. That is Ly Lz plus IR into, this term can be multiplied with L both on the numerator and denominator. So it becomes Ly divided by Lz into sin H root of Ly Lz. Similarly, the current equation becomes VR into root of Ly divided by Lz. We are multiplying this term with L both on the numerator and the denominator. Sin H, it is Ly Lz plus IR into cos H Ly Lz. The voltage equation Vs becomes VR into cos H root of Y, the total admittance, Z total impedance, plus IR into Y by Z into sin H root of YZ. And the current equation Is equals VR into root of Ly by Lz. It becomes Y by Z, total admittance by total impedance, into sin H YZ plus IR into cos H YZ. These are the expression for the sending end voltage and the sending end current.